This is a recreation of my 2021 APS talk, Phase Behavior of Polymeric Microemulsions in Ternary A plus B plus AB blends. This work was done at the University of Waterloo with Mark Matson, and computational resources were provided by Compute Canada. I'll be talking to you today about a symmetric blend of A and B homopolymers and AB diblock copolymers. The blend is symmetric in the sense that homopolymers have the same length, and the diblock has equal amounts of A and B monomers. The important parameters are the lengths of the homopolymers and copolymers, the copolymer concentration, and the Flory-Huggins interaction parameter, which gives the strength of A and B interactions. These blends are interesting because of their tendency to form bicontinuous microemulsions. In this example, the homopolymers are about a fifth the length of copolymers, and the blend is about 10% copolymer. Beyond fundamental interest, bicontinuous microemulsions have numerous applications, including polymeric alloys, nanoporous functional materials, solar cells, and even rechargeable batteries. Microemulsions are fluctuation-induced structures, meaning that in order to get them to appear in our simulations, we need to include compositional fluctuations. This introduces another parameter, the invariant polymerization index, which gives the strength of fluctuations. Throughout this work, we'll try to mimic what's done in experiments and use copolymers that are 5 times longer than the homopolymers. We'll also generally use an n-bar of 10 to the 4. Before we get to our simulations, let's take a quick look at what mean field theory has to say. This is the mean field phase diagram. It's given in terms of the Flory-Huggins interaction parameter and the amount of copolymer. I have inverted the vertical axis so that the high temperature behavior is on top. At high temperature, or equivalently low Ki, the blend mixes into the mixed disordered phase. When the blend is cooled, if there's no copolymer present, the homopolymers macrophase segregate at Ki equals 2. As copolymer is added, segregation is suppressed and the transition follows the Scott line. The Scott line then terminates at a Lifshitz point. At higher copolymer concentration, the blend microphase segregates, forming the lamellar phase. Between these two limiting behaviors, there's three-phase coexistence. Experiments see a similar overall picture: mixed disorder at higher temperature, macrophase segregation at lower copolymer concentration, and lamellae at higher copolymer concentration. Rather than a three-phase region, however, experiments report a channel of microemulsions. This is odd because the real phase diagram should evolve continuously into the mean field one as n-bar goes to infinity. It's difficult to see how this is possible, particularly where does this three-phase region enter? To investigate this discrepancy, we look at horizontal slices through the phase diagram, which is to say we conduct sets of simulations at fixed Chi and scan across phi bar c. We use field-theoretic simulations because particle-based simulations would be too computationally intensive. To understand how field-theoretic simulations work, we can start by thinking of polymers as thin elastic threads. We can then write a partition function for the system as a functional integral over all possible polymer configurations, weighted by their stretching energy. We've included a delta function that sets the total A and B concentrations to 1 and a Boltzmann weight of the AB interactions. Once again, Chi is the strength of these AB interactions. We can't actually evaluate this integral, but we can perform an exact mathematical transformation, converting from a particle-based model to a field-based model. The partition function is now given by a functional integral of an effective Hamiltonian over two fields. W- is a real-valued field that couples to the difference in monomer concentration, and W+ is an imaginary valued field that couples to the total monomer concentration. The effective Hamiltonian is given by an effective Hamiltonian for non-interacting polymers subject to the fields, and an integral over the fields. We still can't evaluate this analytically, but it does allow us to conduct simulations. Given the model I've just described, we can evolve the fields using Langevin dynamics. The evolution contains a deterministic part, related to derivatives of the Hamiltonian, and a random part, a Gaussian noise. This method is not without its difficulties. The W+ field is, as I just mentioned, imaginary. This leads to a complex Hamiltonian. In addition to requiring one to use complex Langevin field-theoretic simulations rather than the usual variety, simulating W+ can also lead to numerical instabilities that are difficult to deal with. We take a different approach in order to sidestep this issue. Instead of actually sampling W+, we can approximate it by its mean field value, and only sample the composition field W-. This approximation turns out to work well in a number of different scenarios, and this includes block copolymer simulations like ours. Now that I've set up these simulation techniques, I can show you some results. As described earlier, we start with a horizontal slice through the phase diagram. We fix the Flory-Huggins parameter, Chi, and we vary the copolymer chemical potential in order to control the copolymer concentration. We start these simulations from either an A or B rich configuration or a modulated disordered structure, which is microemulsions. The A or B rich phases are stable at low chemical potential and have low copolymer concentrations, and the microemulsion is stable at higher chemical potential and has a higher copolymer concentration. In between, there's a jump in the amount of copolymer. This indicates coexistence between the A and B rich phases and the microemulsions. We also did similar calculations at higher Chi-N looking at AB-Lam coexistence, but they're not shown here. Now that we know what each of these configurations looks like, we can directly simulate three-phase coexistence by splicing the configurations together and running simulations in the canonical ensemble. Such a splice results in a configuration that looks like this. Note that this box is quite huge. It represents over 100 million molecules. This would be near impossible with particle-based simulations. Simulations like these give us access to interfacial properties such as widths and interfacial tensions. The details are not shown here, but they are available in our paper. Allowing the system to relax in this way also lets material exchange between the different phases, allowing them to adopt their equilibrium configurations and compositions. We can take a closer look at the composition by averaging over this YZ plane. This gives us the copolymer concentration as a function of the x position. We can clearly see the A and B rich phases with low copolymer concentration and the microemulsion with higher copolymer concentration. Also note the high concentrations at the ends. This is the result of using periodic boundary conditions. Fitting these concentrations allows us to extract the amount of copolymer in each of the phases. The A and B rich phases are about 7.3% copolymer and the microemulsion is about 8.2% copolymer. If you initialize a blend between these concentrations, it'll macrophase segregate into the A rich phase, the B rich phase, and microemulsions. That is, three-phase coexistence. These concentrations therefore give us the limits of the three-phase coexistence region. From that fit that I just showed you, we get 2 points. We can put those points in the phase diagram as part of this three-phase coexistence region, the 2 points at the bottom here. Repeating this procedure allows us to map out the AB microemulsion three-phase coexistence region. As we decrease Chi-N, the three-phase region converges to a critical point. Beyond this is the Scott line, which we find using finite-size scaling. We can also use hysteresis loops to determine the Lam-Dis transition, and we can map out the AB-Lam three-phase coexistence region using similar hysteresis loops to the ones that I showed earlier. Our phase diagram resembles the mean field phase behavior with some notable differences. Segregation is suppressed by fluctuations, as we would expect. The suppression is stronger for Lam-Dis transition than for the Scott line, so rather than intersecting the three-phase region at the top, it hits further down, dividing it into AB microemulsion and AB Lam regions. Comparing our result with experiments, the big difference is that we don't see their microemulsion channel. Instead, we see this three-phase coexistence region. We believe that the simulations are correct, and this difference can be explained by metastability effects in experiments. These structures evolve very slowly. Macrophase segregation is particularly slow due to large length scales over which polymers need to migrate. This combined with the small free energy cost of the microemulsion deviating from its preferred domain spacing, it's easy to see how squeezing excess homopolymers out of the microemulsion to create these A and B rich regions may simply not have occurred in the time over which these experiments were conducted. In this talk, I've described our application of real Langevin field theoretic simulations to ternary blends. We use these simulations to examine the microemulsion state, particularly looking at three-phase coexistence between microemulsions and A and B rich macrophases. This allowed us to map out the topology of the phase diagram for symmetric ternary blends. There are some notable differences between the topology that we found and that seen in experiments, but we think these discrepancies can be attributed to metastability issues in the experiments. These structures evolve very slowly, and it seems likely that the system simply did not have enough time to macrophase segregate into three-phase coexistence. Thanks for listening. For more information, I invite you to check out the paper, and I'll be happy to take any questions. This brings me to the end of the original APS talk. You of course can't ask questions live like they could at APS, but you can leave them in the comments.